Now, this swivel here is a collar. So in other words, it's on the outside of this stick, if you like. So that it will rotate it without doing this. So it's free to go up and down. So you know when this goes fast, it's going to swing out, right? So if you have two weights, if you like this, if you swing fast, it starts lifting, right? The lift started lifting, then it lifts the collar up. When you lift the collar up, you can gear that to the input to the steam engine, and therefore it shuts the steam engine, reduces the steam input, and then the engine runs slower. And then if that's too slow, this thing will come down here, and then this would now give you more engine. It's an automatic control. The engineer that drives this didn't have to take care of the speed at all. This little gadget. Now, the fascinating thing for me, this is completely, you can think of the whole thing as an entirely mechanical system. No measurement involved, no calculation involved. And that's what Perrine design of a circuit does. It's a quantum mechanical thing. It will run itself. It doesn't have to have a classical measurement. Okay, so we have both. This is very famous. This is what gave us the quantum equivalent of classical computer. The computer you now works so accurately. It's not luck. It's you know, they do copies. But since we can do parallel copies, quantum computer can be much faster, even error correction. So that's a big business in computer science and engineering is error correction. And this models on that. So part of it is quantum mechanical make it fast. Part of it is just as slow as the microprocessor, although you think microprocessor is pretty fast because it's measuring things. This circuit promises that no measurement. Take all this speedometer stuff out of it. There's an effective way to do that. So now the challenge is actually to make it. But this is a wonderful idea. Of course, the gem of the idea doesn't come from us, but from other people who say that you should be able to do this. But this, he has a clever idea in doing this. So that's the kind of thing we're doing. It's very exciting, but it's also very interesting how, you know, historically we have this gadget, and then we develop this, and then we copy this, and then we say, well, we'll develop it back. It's actually copying of a steam engine governor. Now we talk a little bit about this measurement. Now, why do I want to talk about this? So it's an idea that will bring us to the next point, which is what is reality? And why didn't it happen? Why didn't we worry about this? Actually, we worried about it before. But for a physicist with no Newtonian mechanics, we say, we don't need that. We know reality because Newton tells us how exactly to calculate it in principle, like the heads and tails of the coin. Now, here's another quantum coin. It's an electron or an atom. The electron itself has some mass, although it doesn't have radius. It does spin. So it's like a ball, like baseball, if you like. If you throw a baseball, you know, it's hard to hit because you can spin it and therefore make a curveball, or ping pong ball. A ping pong ball, you can really spin it, right? And then you go like this. It has two possible directions in any axis. It either points up or down. So we can represent that by H and T, two states. So so this is an oven with an atom that produces an atom in which has one electron, one active electron, and that active electron can point either up or down, or a linear combination of the two in quantum mechanics. Now, how do you know that? There was a classic experiment that was done. You put in a magnet. Well, for those of you who know some physics, you know that this is a little magnet. So this little magnet gets attracted by the big magnet. So if it points this way, it would go that way. If it points the other way, it goes that way. Now, how do we describe that in quantum mechanics? We call it plus or minus. Remember, we have just an addition of two vectors. Think of this as two vectors. One represents up, the other represents pointing down. And then the center of gravity, where the position of the ball is the same, right? Because it's the same ball. But now when you split it, they're different. This is called entangled state. So that's the whole, there's another story of Einstein. He says that that's a paradox. Well, now you'll see, what is the problem there? So it says, well, so here, by the time you get to here, I know that this guy is here, which is up. Then its spin of the ball has to be right-handed, point up. If it goes down, it has to point down. So it's a great measurement. Quantum mechanical description is that there's a 50% chance of this or 50% of chance of that if I put alpha and beta equal to 1. How do we describe that? We say, well, it has 50-50 probability, or in this case, it's the square of this thing, the probability. Those are two possible outcomes. That's fine. But what we don't have is a description of how this comes to be. Because we said, once the probability happens, it will be either up or down. How do you describe the fact that it will land here? Or it will land here, but not there? There's no way to describe it. People have tried, you know. So that's, I call that the readout problem. What is a readout? We are sentient beings. We can actually see that, but it has nothing to do with it. You can use a videotape and tape this thing at some time, and then you can show it to everybody. Everybody will see it all at the same time because it's videotaped that this one is bright, this one is dark, or vice versa, when you have only one atom going through it. But how? When, where does it decide, instead of having this whole state, that it becomes only this one or only this one? That's an impossible thing. So that's called a readout, because at that point you can see it. So that's a readout problem. It's normally called a measurement problem. But you see, doing it this way, I didn't invent this. Actually, it was in Von Neumann's book.